Okay, I got 3:40, so let's go ahead and begin. Okay, if you are interested in my office hour today, please let me know. It's 6 to 6:50. Okay, I'll make another example, another announcement at the end of the period, at the end of the class. We're going to go over 16.3 today. Okay, fundamental theorem of line integrals. Okay, 16.3 notes. Okay. The fundamental theorem for line integrals. Okay, and as always, these notes are going to be posted on YouTube, on my YouTube channel for Santa Ana College. Okay, does anybody have any questions before we begin on anything? Just let me know.
Oh, did you mention about the final? This one I was saying on the other day. So the final exam, that you're gonna change a format for it?
It'll be take home.
Oh.
So I mean it won't be timed, is what I'm saying. Okay. Yeah. Okay, fundamental theorem of integrals. Okay, let C be a smooth curve given by the vector function R of t.
Not factor, but
Okay, where t goes from A to B, let F, okay, let capital F be a differentiable function is that capital? I think then it's actually lowercase f. Yeah, this is lowercase f actually, sorry. Lowercase f. But lowercase f be a differentiable function of 2 or 3 variables whose gradient vector okay, delta f is equal to f, capital F. Okay, whose gradient vector delta f equal to f is continuous on C. Then the line integral of C over C of f dot dr is equal to the line integral of the gradient of f. So we're saying that there exists a function f, lowercase f, that I can take the gradient of that, and that is my my vector, that's my function capital F. Okay. So in order to go from f to gradient, in order to get lowercase f here, okay, I'd have to take an integral, but it'd have to be the opposite of the partial on x and the opposite of the partial on y. And we'll get to how that works in a little bit. Okay, and so the f is going to be the gradient of some other function. We might call that the parent function. We might say that this guy is the parent, and this guy here is the child. Okay, because if we do a partial derivative on the parent function, then we will get the child function. Okay, we're saying that there exists a parent function such that if I take the gradient of that parent function, I get the capital F function. Okay, so it's kind of a little different in that capital F is not the capital F is the gradient. It is not the antiderivative. So if you think back to antiderivative, you think back, oh yeah, capital F is my antiderivative. That's not the case in this case. It's reversed. Okay, F is really, if you think about it, the anti of the partials. Okay, so this is gradient F dot dr, and this will become a lot more clear as we go through these examples. Now, if this is true, if there exists, okay, if there exists a function f, okay, such that when I take the gradient of f, I get equal to, okay, my force field or my vector field. Okay, so I have this force field, and if I can find a parent function for this, okay, then I can write it as such that the line integral over this parent function, the gradient of this parent function is equal to dr. Now, if this parent function exists, it makes my integration really easy, because then I can just say, well, there's going to be some sort of limits of integration, okay, of c in terms of t. We're going to parameterize this, okay, with respect to r of t. Okay, we would parameterize f in terms of r of t. So we would get a to b of f of r of t, okay, of r prime of t dt. Okay, and if this is the case, this is going to be the gradient of f. Sorry about that. Let's put the gradient in there. And if this is the case, and then I can almost think of the gradient as the derivative, and we're taking the antiderivative of the derivative. And so if we take the antiderivative of the derivative, and this is a dot product right here, sorry about that. If we take the antiderivative of the derivative, we just get out the original function, the parent function. And so this is going to then equal the parent function evaluated at r of b minus the parent function evaluated at r of a. And that is my fundamental theorem of line integrals. Okay, so we're using this idea of gradient of the partials, and then over this line integral, okay, we're turning this force field into this vector field into the gradient of a parent function. If I could do that, then I could just use basically the fundamental theorem of calculus to do this. Now, I don't want you to take this based on faith. Let's prove this. Okay, let's go ahead and prove this. Let's do a proof. Okay, so we have the gradient of f, okay, parent function, okay, dr, is equal to, okay, a to b of the gradient of f, r of t, dotted with r prime of t, dt. My d is messed up there, dt. Okay, what does this mean? What does the gradient of f look like? Well, it's the partial derivatives, okay, over this vector field, which is going to be the partial derivatives of a standard basis vector. Right? We say, well, we have some sort of x of t, y of t, z of t, and for the x of t, y of t, z of t, we're going to have, okay, these partials. The gradient is going to be the partial of f with respect to x, and we'll have that in the x direction or the ith direction. Okay. And then this is going to be plus the partial of f with respect to y plus the partial of f with respect to z. This is j and k. Okay, so that's my vector. Okay, this is my gradient vector. Move this up, a to b. Okay, I'm going to dot this gradient vector with r prime of t. Well, I'm just going to say that r of t, okay, let's say that r of t is equal to x of t I plus y of t j plus plus z of t k. Okay, so we're going to say, hey, you know what? Whatever x of t is, whatever y of t is, whatever z of t is, this is, okay, this is r of t. And so if we want to take the derivative of that, well, it's just the derivatives of them. So it should just be x prime of t or d x dt, okay, I, plus dy dt j plus dz dt k. Okay, and then the dt is on the end here. Now this is the dot product. So the dot product, we're going to multiply component with component and then sum them all up. So we get the partial of f with respect to x dotted with dx dt. Okay, plus, now where'd my I go? Well, remember when we do dot product, we're dropping this vector. When we do dot product, we go from a vector to two vectors to a scalar. So we're dropping the vector notation of the standard basis because it's no longer going to be a vector. It's going to be a scalar. Okay, plus, okay, and then this one goes, the two middle ones get multiplied, df dy, I'm sorry, partial of f on y, dy dt, okay, plus the partial of f with respect to z, dz dt. Okay. And then all of that is going to go from a to b with respect to t, dt. Well, this should look very familiar. Okay, this here, okay, is the chain rule. Okay, so this is the chain rule. So we would say that this would be f prime of r of t. Okay, f prime of r of t. So this would be f prime of r of t. Okay, but what are we doing with that f prime of r of t? Well, we're doing a integral from a to b of dt, right? So if we were to take the chain rule of this thing, right? So the chain rule, if we were to take the derivative of, this actually is not f prime of r of t, this is f of r of t prime. Let me do it like this. It's the whole thing. It's the d dt of the whole thing. It's the, take the derivative of the whole thing, and that will give you the chain rule, right? I don't want just the derivative of the outside. I want the derivative of the outside and the derivative of the inside. Okay. Because what's that going to give me? What's the derivative inside going to give me if I do that? Well, it's going to give me, you know, using the chain rule here, it will give me the what's above. Let me do the intermediary step here. Okay, just so that we're not missing anything. So the intermediary step is this. What is this thing as the chain rule? Well, it's this guy here. It's going to be f of f prime of t, right? Dotted with r prime of t. Okay. It's basically that's what we have before, but we have the gradient. So it works. Okay, so it's now to the derivative of the outside, okay, dt. And so the idea is that this thing, okay, this thing is going to become, it's no longer dot. This thing is going to become this. It's going to become d dt of this parent function r of t, okay, dt. And so we're going to take the derivative and the integral with respect to t. So using fundamental theorem of calculus, this was, okay, this was by chain rule. By chain rule. So by FTC, okay, it's fundamental theorem of calculus, I can cancel out those dt's. And so by taking the derivative of the integral, well, what does happen? I take the derivative of this thing, but then I integrate and I have limits, and this thing just becomes f of b, okay, f of the upper limit, okay, actually it's f of r of b, sorry, f of r of b minus f of r of a. Okay, and that's your kind of your proof there. Okay. Okay. Let's look at an example of this. Okay, number one, find. I bring that down. Okay, find the work done by a gravitational field okay, f of x is equal to negative mg over, okay, and this is a bold x, which is kind of confusing, but this is the way the book uses it, so I'm gonna go with the way that the book uses it. Okay, this is a bold x. This is actually a vector x. Now, I would probably have changed it to a different letter, but I want to be consistent with the book. Okay, I might have changed it to W or maybe even V for vector. Okay, maybe I'll do that just to make it a little less confusing. Yeah, let's just do that. Let's let it be V for vector. Okay, this is a vector, and it's vector V, and it's cubed times vector V. Okay, where V is a vector, and again I can make it a vector by just putting the vector symbol on top of it. The book makes it a bold X, which I have no idea why they used X for the vector, but I think just because instead of, right, so this is now f of v. Okay, so the idea here, okay, is that this is the, you know, how two bodies navigate gravitational force on each other. So we've got the mass 1, mass 2, and the gravitational constant. Okay, and so we want to find the work done by a gravitational field as such. Okay, and moving a particle with mass m from point from the point 3, 4, 12, okay, to the point 2, 2, 0, okay, 2, 2, 0, such that, okay, v, vector v is equal to x, y, z, okay, some sort of vector x, y, z. Okay, don't know what that is, but okay, and okay, we'll say f of v, okay, capital F of v is equal to the gradient of some f, okay, where, okay, m, where f, the parent function here, is going to be mmg over basically the magnitude of v. It's going to be over the magnitude of v here, which is x squared plus y squared plus z squared. Now, why would that be the case? Okay, that would be the parent function of this thing. Okay, well, if I take this parent function real quick, mg, okay, over this guy here, v, right? So, which is equal to, we could say there's two m's, lowercase m and capital M. They're kind of looking like the same here. Let's fix that. Okay, mmg over, we'll call this the magnitude of v. Okay, so that's the magnitude of vector v. So if we take that parent function, magnitude of v, okay, which is the square root of x squared plus y squared plus z squared, and we take the gradient function of that. Okay, so now what's the gradient of this thing going to be? Well, this is going to be on x. Let's do f on x, f on y, and f on z, right? Okay, so let's take the gradient of this. Okay, so then what are we going to get here? Well, we're going to get, okay, the gradient of f is going to be equal to, okay, let's take the derivative with respect to x first. So this is going to be 2x on the top. So this is mg 2x over, take the derivative, that 2x comes from the chain rule. Let's do the derivative of the square root is 1 over 2 square root, right? So this is 1 over 2 square root of the same thing, x squared plus y squared plus z squared. And then what's the derivative of the inside? Well, it's just with respect to x, it's going to be 2x. So you can see that these are going to cancel each other out, right? Okay, except there's a problem here. What am I doing wrong? Oh, that's the problem. Okay, it's not the square root, it's the square root of the bottom. Okay, this is just a constant. So let me rewrite this as this. mmg over times mmg times x squared plus y squared plus z squared to the 1/2, right? Okay, so now this makes more sense. Okay, so no, negative 1/2, my bad. Okay, so now bring down the negative there. That's where we get the negative from. That makes sense. Okay, so now bring down the negative 1/2. So this is mmg, okay, times negative 1/2. Okay, this is now going to go to the negative 3/2. There we go. That makes a lot more sense. Okay, to the negative 3/2. Okay, so x squared plus y squared plus z squared to the negative 3/2. Okay, so this is equal to now, okay, times chain rule. Don't forget chain rule. This is going to be 2x. Okay, if I take my, with respect to, right? So let's do this. This is going to be f sub x is going to be this guy. Okay, so again, the 2's cancel out. I get a negative, and it's negative 3 over 2. So this is negative, okay, f sub x is equal to negative mg over x squared plus y squared plus z squared, okay, to the 3/2 power. Okay, so again, if you're taking the gradient of this thing, okay, then this is going to be, oh, and don't forget the x here. This is x, right? Okay. Okay, and then what about the other ones, right? The f sub y, f sub z, they're basically going to be the exact same thing. Okay, f sub y is going to be negative mg y over this thing here, okay, which is going to be the square root of x squared plus y squared plus z squared cubed. There's a reason I'm going to write it like that. And then f of z is the same thing, negative mg, okay, z over this thing, square root of x squared plus y squared plus z squared cubed. Okay, so now if I look at this gradient, I have basically the same thing, okay, in the front of each of these, except we have the, oops, okay, we have the y, we have the x, the y, and the z, right? So the gradient is still a vector, but I can factor out what they have in common. I'm going to factor out what they have in common and put that in front. So this is the gradient of f is equal to negative mg, okay, over, well, this is, what is the square root of x squared plus y squared plus z squared? Well, that's the magnitude of v. Okay, that's the magnitude of v cubed. And then what would I have left over? Well, I'd have my x, y, z. Well, what was x, y, z? If I factored that out, this magnitude is going to be some value, right? This is going to be a value. So again, turning a vector into scalar, magnitude is a scalar. Okay, and so what is this thing here? Well, that thing goes back to v. So negative mg over v cubed to v. Okay, so that was just a kind of a proof to say, hey, we know that if we're given this function as the parent function, then it's going to provide, okay, this, if I take the gradient of that, I get this guy as the child function, okay, which is my gravitational field that I'm working with. Okay, so that's kind of like a mini proof of, I mean, I didn't really have to go into all that, but I think it's good to kind of see the logic behind it. Okay, so if we have this guy, and we want this guy as our f, as our parent function, then, well, how do we get the distance, or sorry, find the work? How do we find the work? Well, what was the work? We saw from Monday that the work was the line integral of f dot dr, right? F dot dr. Okay, and so because this f can be changed into a gradient function, which we're going to call conservative later, okay, if you can get a gradient function, then it's conservative. Okay, and if this is conservative, then this gradient function exists, dr, then what do we know? Then we know that we can just go from f of r of b, right, minus f of r of a. But okay, so what's r of a and r of b in this case? Okay, so we have to kind of think, well, what do we have? We have r as x, y, and z, right? R was equal to x, y, and z. Okay, so there was that vector, x, y, and z. Okay, so in this case, well, what do we have? Or we could say v in this case, right? Okay, I mean, really, it's kind of we're doing with respect to v. Okay, was vector x, y, z. And so now what are we saying? We're saying that this thing, okay, we're going to take it from vector. Well, let's do it this way. We're going to say f of this vector, call this vector v, vector v. Okay, evaluated from b. Well, what is b? B is my x, y, z of my first point. Okay, so I'm just going to say it's f of, okay, b. Well, what was b? B was my second point, right? So a, what was my first point? It was 3, 4, 12. What was b? B was my second point at 2, 2, 0. And so I'm just going to say, hey, okay, given that this has a parent function, we proved what the parent function was. Okay. And we said that there does exist a parent function, right here. So what is that parent function? Well, given these values for x, y, and z, okay, it's going to be mg over the square root of x squared plus y squared plus z squared minus, right? And this will be, you could do a sub 2 or whatever. But this is of my first point. I'll just plug in the values here. Okay, this is 2, 2, and 0 minus mg over the square root of 3 squared plus 4 squared plus 12 squared. Okay. So this thing is going to be equal to, okay, mg over, this is going to be the square root of 8, minus mg over the square root of 169. Oh, okay, so just factor out the mmg, okay, and this is going to be 1 over 2 radical 2 minus 1 over 13, and I can just leave it like that. So that's the work done over this line integral. Okay, let's do a theorem, and then we're going to do another proof. Okay. So theorem. Okay, let f equal pi plus qj be a vector field on an open simply connected region D. Okay, suppose P and Q have continuous partial derivatives, first order partial derivatives, okay. Just like those guys in Star Wars, they're the first order. Okay, first order, I can't write. First order partial derivatives and okay, the partial of P with respect to y is equal to the partial of q with respect to x, if this is correct, okay, throughout D, then we say that F is conservative. Then F is conservative. Okay, so this is saying that we're doing kind of a proof backwards. We're saying that, and we'll get to this in a little bit. We're saying that this is the converse of really what we want to prove. Okay, we're getting the converse statement of really what we want to prove here. Okay, so we're saying that if we have a simply connected region D, okay, D here, and we have P and Q have continuous first order partial derivatives, we have all this set up, and then we have the partial of y with partial of P with respect to y, and the partial of Q with respect to x. If all of that aligns, then F is conservative. Okay, then F is conservative. Meaning, what does that mean? What does it mean to be conservative, though? Okay, well, okay. Okay. F is conservative. Okay, on D. Okay, if there exists, okay, if there exists a function F, we already kind of alluded to this, function F, such that the gradient of F is equal to big F. Okay, so again, if this big F, if this little f occurs, if we can get little f, then it's conservative. Okay, that's kind of the crux here. Okay, let's talk about another theorem, and then we're going to do a proof. Okay, just to, because we're going to go forwards and backwards on this thing. We're going to say, hey, certain conditions, then it's conservative. If it's conservative, certain conditions. Okay, another theorem. Okay, if f of xy equals p of xy I plus q of xyj, okay, is a conservative vector field, okay, if it's conservative, then, okay, then we have this is the case. If it's conservative, again, what does it mean to be conservative? Okay, I'll just put that in parentheses. What does it mean to be conservative? That there exists F such that, okay, F, the force field is equal to the gradient of F. Okay, there exists some other vector field, that's the parent, okay, of this. That's what it means to be conservative. If it's conservative, then what do we know? We know that dp over dy is equal to dq over dx. Okay, so this is this direction. Okay, so we've done it forwards and backwards. Basically, this is going to be the crux to help us figure out, is it conservative? And then if it is conservative, then we can find F. So the question that we're going to ask is it conservative? And the second one is, then what is F, little f, right? And what's F? Okay, is it conservative? And if it's conservative, then what's F? Well, if it's conservative, that's true. True if conservative. Okay, and if this is true, right, if it's conservative, then this is true. And if this is true and it's a simple region, okay, it's not got any holes or any weirdness to it, then it's conservative. So it's forwards and backwards, okay, as we saw here. Okay, so it's basically, it's two theorems in one. Basically, you're going forwards, you have that criteria, you're good, then it's conservative, okay, on a simply connected region. Any conservative vector field is going to have that. So if they give you conservative, you know that the relationship, this equation of partial derivatives is true. If it's a simply connected region, it's a very nice region. They give you that and that this is equal, then it's conservative. Okay, that's the basic crux to this whole thing. Okay. Okay. So let's determine. Let's do an example here. Example 2. Okay, determine if f of x, y, okay, determine if f of x, y, okay, equals 3 plus 2xy I plus x squared minus 3yj, 1 is conservative. Okay, is it conservative? 2, well, let's do 1 first. Okay, if it's not conservative, all bets are off. We can't do anything. Okay, we can't use the fundamental theorem of line integrals because it's not conservative. There is no parent function to work with. There's no parent function, all bets are off. Okay, determine if this is conservative. Conservative. Is it conservative? Well, let's see. Let's take well, what's p in this case? P is the function in front of I. Okay, so p of xi here is equal to 3 plus 2xy. Okay. What's q? Q of xy is equal to x squared minus 3y. Oh, okay. So now I want to know, is this conservative? Well, if it's conservative, then that relationship is going to hold, right? Okay, this dp dy is going to equal to dq dx. Okay, partial of p. Okay, so what is the partial p with respect to y? Well, wouldn't it just be 2x here? And what's the partial of q with respect to x? Well, wouldn't that just be 2x? So is it conservative? Yes, it's conservative. Okay, so what does that tell me? Well, that tells me that since it's conservative, that there must exist an f, there exists f such that capital F is equal to the gradient of f. Okay, so there exists a gradient. When I take the gradient of that function, I get the original function here. So that begs the question, well, what is f? Right, what is f? Okay, so find f. Find a little f, okay, lowercase f, the parent function. Okay, so f is going to be equal to f sub x. Nope, wrong way. So f sub x is going to be equal to this thing here, which is going to be 3 plus 2xy, and f sub y is going to be equal to x squared minus 3y, right? Because f would be the gradient of f. So if I took the partial of f with respect to x, I would get this first component. If I took the partial with respect to y, I would get this second component. Okay. So how could I figure out what f is? Well, let's integrate, but only integrate on x for the first one here. So I'm going to say f of xy is equal to what? Well, integrate with respect to x. I get 3x. Okay. Plus x squared y. Right? Integrate with respect to y. Plus, don't forget my constants here. Well, what could have been my constants? Well, my constants could be anything involving y and a constant. So I'm just going to say, okay, this is going to be g of y plus k. Oh, okay. So how did I get this? I did the partial integration of x, of f sub x. Okay, let's do the partial integration of f sub y. We're basically trying to solve a puzzle, like what is the parent function that will give me these partials? Right? Okay, so this f sub y was equal to x squared minus 3y, x squared minus 3y. Okay. So what's the partial integration on y here? Well, isn't that x squared y minus 3 halves y squared? Just check here. No, it's y cubed over 3. Okay, this should be squared. I think I messed up. It should be y squared. F sub y. Yeah, this should be a y squared. Sorry about that. This should be y squared. Okay. So I want them to be the same. Okay, y squared. Okay. Okay, is that going to change anything here? No, they're still going to get the same 2x. If I take dq dy, okay, perfect. Okay, so this is x squared y minus, okay, y cubed, okay, plus, and I'll call this, I don't know, j of, I don't want to use j. Let's use b of x plus, and I'll call this, instead of k, we'll call this L. I don't know, just some other constant. Okay, so this is f of xy. Okay, well, let's kind of look at the pieces of the puzzle that we've come up with here. Okay, so we have f sub xy is equal to, well, look at this. They both have this x squared y. So that's a function involving x and y. Plus, they have this function involving only x, which when I took the partial on that with respect to y, that would disappear. And that's this guy here. That's the 3x. That's the b of x. So this is 3x. Plus the g of y. Well, what's the function that only involves y over here? Well, it's this one here. And if I took the partial with respect to x of that guy, he would disappear. So this is going to be minus y cubed, right? So that's y cubed plus some sort of constant. Okay, plus some sort of constant. Okay, so that gives us that. Now the third, let's find the line integral. Let's find the line integral. The line integral of what? Well, okay. Okay, let's use this idea to find the line integral in the fundamental theorem of line integrals. Okay, because what did we do? We went through the work of finding out what f was so that we didn't have to integrate. Okay, so that's the idea here. Okay, so find the line integral of f dot dr if r of t is equal to e to the t sine ti plus e to the t cosine tj. So it's my vector. And then we're going to have t go from 0 to pi. Okay, so t goes from 0 to pi. Okay, and so what? Well, we know that one, it's conservative. Is it conservative? Yep, it's conservative. Is it conservative? Yes, check. Is there a parent function? Check. Okay, and so now what do we do? Well, this is going to be, okay, using the fundamental theorem of line integrals, this thing is going to go be equal to f dot dr is going to be equal to f, the gradient of f dot dr, which is going to be equal to what? It's going to be equal to a to b, right, of this function. I'm just going to put quotes in here from before, dt, right? And then what is that going to give us? That's going to give us f of r of b minus f of r of a. Okay. And so what does this tell me to do? It tells me that, okay, this is going to be f of r of b. Well, what's b in this case? This is now a parametrized function in terms of t, right? So in terms of t, well, what's b? What's my upper limit on this a and b? Well, dt would go from 0 to pi, right? So I would be plugging in r of pi minus f of r of 0. Okay, so now I'm just going to evaluate this. Well, what's r of pi? Okay, let's see what is r of pi. Sorry, this is a little small. Okay, r of pi, well, plug it in. This is going to be e to the pi sine pi I plus e to the pi cosine pi j. Okay, so this is going to be e to the pi sine pi. Well, sine of pi, that's 0, right? Okay, so that's 0. Okay, so that's going to go to 0. What about this one? E to the pi cosine I, that's -1 times e to the pi, so this is negative. This is going to be 0i minus e to the pi j, right? Yep. Okay, and so that's what r of pi is. I'm going to write this in component form. Just say that r of pi is equal to 0 and negative e to the pi. Okay, now what's r of 0? Plug that in real quick. Okay, well, what's the sine of 0? The sine of 0 is still 0. Okay, right? So sine of 0 is 0. So e to the 0 is 1. So this is still going to be 0. Okay, that's 0. And then what's the cosine of 0? Well, that's 1 times e to the 0. Well, what's e to the 0? It's 1. So 1 times 1 is 1 if you went through and evaluated that. So now what's f? Well, what was my parent function? My parent function was this thing here. And if I bring this guy down, okay, so we have f of xy equals x squared y plus 3x minus y cubed plus k, right? Okay, so let me expand this. And so the idea here is that we have f of r of pi, right, minus f of r of 0, okay? So what was r of pi? Well, it's 0 when x is 0, y is negative e to the pi. And for r of 0, when x is 0, I'm sorry, x is when t is 0, r x is 0, and y is 1. Okay. So now we have our f of x, y is equal to this guy. Well, I already wrote it there. Okay, is equal to this thing. So all I'm going to do is plug in my limits. Okay, plug in my x's and y's. So this is going to be 0, negative e to the pi, 0 squared times negative e to the pi. Okay, plus 3 times 0 minus e, negative e to the pi cubed plus k, where the k is going to drop out here. Okay, minus, okay, and then for the second one, it's 0 for the x's, so those are both going to go to 0. And then we're just going to have 1, right? So it's a minus minus 1, so it's a positive. So this is going to be, well, let me just not skip over it, work it out. So 0 squared, 1 times 1, plus 3 times 0, plus 1 cubed, okay, plus k, right? So that goes to 0, that goes to 0. This becomes e to the 3 pi, right? And then the minus becomes plus 1. And then what happens to the k's? Well, the k's drop out because it's k minus k, which is 0. And that's the answer. Okay, so we were able to find the line integral. If that thing exists, if it's conservative, this is a great test, right? If it's conservative, then this works. Okay, if it's conservative, then this is true. Okay, that's our first step. Okay, if it's a simple curve and it's conservative, then that is true. Okay, great. That means that the parent function exists. Okay, so then we do the antiderivatives to find the parent function, the anti-partial derivatives, I should say. So then find the parent function. And then once we find the parent function, we can actually do the line integral by using the fundamental theorem of calculus, fundamental theorem of line integrals. Okay, so let's prove something using this in physics. Okay, let's do a proof of something in physics using this idea. Okay, so in physics we have force equals, I don't know why this is so small. Okay, force equals mass times acceleration, right? So I'm going to say that this acceleration is the second derivative of my position vector. Okay, so this is the second derivative of my position vector. Do you agree? This is right. So what's the first derivative? Velocity. What's the second derivative? Acceleration, right, of our position vector. Okay, so what's force here? Force is equal to mass times r double prime of t. Okay, so I want to know what's the work done here. Okay, in my line integral over this force field, okay, over this vector field, okay, with respect to r, okay, with respect to my position. Okay, so what's the line integral going to be here? Well, this is going to go from A to B. Okay, excuse me. Okay, of, this is going to be f, capital F, of r of t. Okay, now a function of t. Okay, dotted with r prime of t dt. Okay. Okay, nice. Good. Okay, and so now what are we going to do? Okay, we're going to take and replace this, okay, f of r of t with this thing here. This really should have been f of r of t, right? Okay, it's the force with respect to the position vector. I got to write that better. F of R of t. Okay, is equal to mass times acceleration with respect to R of t, position vector. Okay, so this thing, okay, I'm going to replace. Just going to sub this in. Okay, you've been subbed in, sir. Okay, m r double prime of t dotted with r prime of t dt. Okay, nice. Okay, I'm going to pull the m out in front. This is going to be a to b. Okay, and this is the dot product, by the way. This is going to be r double prime of t dotted with r prime of t. Okay. Well, now I'm going to do something a little sneaky. Okay. I'm going to rewrite this as 1/2 times 2 r double prime of t dotted with r prime of t. And again, this is a little bit of manipulation, but it's okay. 1/2 of 2 of something is still the something, right? It's still the same thing. This goes from A to B, M. Okay, let's pull out the 1/2. So this can be M over 2. Okay, A to B. Okay, and I want 2 of these things. Well, what is that? That's r double prime of t dotted with r prime of t plus r double prime of t dotted with r prime of t dt. Okay, I wanted 2 of those. Why do I want 2 of those? Because this is the product rule for dot product. Product rule. Product. Okay, product rule for dot product. Okay, product rule for what dot product? Well, product rule for r prime of t dotted with r prime of t, right? So r prime of t, if I take the derivative of this thing, okay, with respect to t, then I should get the above, right? So derivative of the first times the second plus the derivative of the second times the first. Say that again. Derivative of the first times the second plus the derivative of the second times the first. Oh, that's nice. Okay, so this is equal to m over 2 a to b of d dt of this thing. Well, what is anything dotted with itself? Oh yeah, we gotta think back. Okay, well, if I have vector A dotted with vector A, what did that give me? What did that give me? Well, let's think about this for a second. Okay, this would be x, y, z dotted with x, y, z, which is going to be x squared plus y squared plus z squared. Okay, so now how could I rewrite this in terms of something else? Well, isn't this, if I square root and then square it, isn't that the magnitude of a squared? Isn't that, oh yeah, that's the magnitude of a squared. Remember that? That was like chapters ago, right? Like, oh yeah, I remember that. Okay. So this is going to be m over 2, okay, a to b of this thing. Well, what is this thing here? It's going to be, and this is dt, sorry. Okay, this is going to be ddt of the magnitude of r prime of t squared dt. Oh, okay, that's kind of cool. Okay. But what is this? Well, from the fundamental theorem of calculus, we can figure this out real easy because we're taking the integral of the derivative and we have limits, right? So the ddt's, right, cancel out, and then I use the fundamental theorem of calculus. Okay, I mean, they don't really cancel out, but you can think of it as they're canceling out. And we get, okay, 1/2 m times r, sorry, r magnitude of r prime of t, or sorry, b, let's plug in our b squared minus 1/2 m r prime of a squared. Okay, so I'm going to call r prime of v, v. Okay, v as in velocity. Okay, as in, I could even call it speed. Well, velocity is the vector. Okay, but this is the magnitude would be the speed in a certain, going in a certain direction. We need the vector to know what direction it is, but the magnitude and then square that, right? So I'm just going to call this kind of like the speed squared, okay, or what we would call in physics our velocity. You just give me a direction and then that's my velocity. So I'm going to call this r prime of v magnitude. I'm going to call that v sub b as in velocity, because the derivative of position is velocity, and that's going to be squared equals 1/2 m v squared. Oh, okay, that's kind of interesting. Minus 1/2 m va squared. Okay, well, what is that reminiscent of? All my engineering friends, what is this reminiscent of here? 1/2 mv squared. Any ideas? Long says kinetic energy. Yeah, exactly. Kinetic energy. Armando says kinetic. Yeah, exactly. 1/2 mv squared. That's kinetic energy. So this is the kinetic energy we'll call at point B minus the kinetic energy at point A. Okay, was equal to what? What was this whole thing equal to? That was equal to the work, right? It would be equal to the work in joules or whatever, however you want to, right? That's the work done. Okay, that's kind of cool. So the work done is the difference in kinetic energy. Oh, okay. Well, let's do something else here. Let's say that this is the change in kinetic energy, right? So this is the change in kinetic energy. Okay. Well, let's deal with the position. Let's let P be position, the position in space of a point P, okay, in space. Okay, so I'm going to say that we have a point P in space, x, y, z. Okay, a position. We could even call this a position vector. Okay, if we wanted to make it a vector, we could. Okay, so this is a position. Okay, and I'm going to say that that is equal to some function, the negative of some function, x, y, z. I'm going to make that the negative. I'm going to negate it. Okay, I'm going to say that the position is opposite some sort of force field. So my position is opposite some sort of force field, like maybe gravity, right? Think of gravity pulling down on me. And what's my position? My position is opposite. So in order to move up, I have to go against the flow of gravity. Oh, okay. So we're going to let this guy be a force field. Okay. So if F is equal to the gradient of little f, then big F is equal to negative the gradient of P. I'm just saying there exists an F such that P is just the opposite of F. Okay, think of it as a negative parent function. If you really want, I could put the negative over here and the positive here, and then it says, oh, there exists a parent function such that I just take the negative of it. Okay, I need a negative to reconcile at the very end. Okay, but it's basically the same thing. We're just saying it's conservative. It has a parent function. There's this parent function where instead of calling f, we're calling negative p. Okay, instead of calling f, we're calling negative p. That's it. It's the only difference. Okay, where P is the potential energy. Okay, and the work done over the force field dot dr is equal to negative gradient of P dot dr. Nice, nice, nice. Okay, which would be equal to, okay, the negative of P of B, okay, I'd say R of B, but there's just B. Think of it as negative P of B. Okay, oh, you do R of B, that's fine. R of B, okay, I'm gonna skip steps. Okay, minus the negative of P of R of A. Oh, okay. So what is this? This is going to be negative of, I'll just call R of B just my position at point B, right? That's my position at point B. So my position at point B dictates my potential energy at point B. Oh, okay, that makes sense. Okay, from a physics standpoint, that makes a lot of sense. My position is, okay, dictates, okay, so this is negative P of B, and this is plus P of A. Oh, okay. So I'm going to rewrite this because I don't like the negative in front. So I'm going to go P of A minus P of B. This is the work done in moving what? In moving a point from A to B. Okay, A to B. And why is the work negative? Because it's going against the force field. Okay, makes sense to me. Makes sense to me. So what can I do? Well, since I just ended up with this equal to the exact same thing, I could set them equal to each other. Okay, so we had, okay, KB minus KA is equal to, these are lowercase, sorry, KB, KA, is equal to PA minus PB. Oh, okay. And so I'm going to swap these guys. And I'm going to say that KB plus PB is equal to KA plus PA. And what is this formula? Tell me. What does that tell me? Any ideas? What law is this? What law is this that tells me that the kinetic and potential at one point is the same as kinetic and potential at
The law of conservation of energy?
Yes, exactly. It is the law of conservation of energy. So we have just proven the law of conservation of energy using line integrals. Okay, so this is the law of conservation of energy. Okay, which is why when we say F equals the gradient of little f, when we say F equals the gradient of little f, given little f exists, then big F is called conservative. Oh. It's not because it votes a certain way. It comes from the law of conservation of energy. Okay. I know everybody's got things on the brain here. Okay, let's try one more example here. Okay. Where did I leave off? Number 3, maybe? I don't know. Lost my notes. Yeah, number 3. Okay, so lots of proofs today. Okay, number 3. If f of x, y, z equals, okay, y squared I plus 2x y plus e to the 3z j, okay, make sure you're writing this down, plus 3y e to the 3zk. Okay, so we have this guy. 3 dimensions, right? 3 dimensions, okay. So I'm not going to ask you if this is conservative. We'll do that later, okay? Because I haven't set up, you know, how to do conservation in for 3 dimensions, and that doesn't come until Monday, okay? When we talk about Green's theorem in 3 dimensions. But I'm just going to tell you that this is conservative, okay? Okay, so given that delta f equals f, that there does exist a parent function here that makes this conservative, given that this and f exists, okay, thus conservative. Okay, find f of x, y, z. Okay, find this. Okay, so we want to do some anti-partial derivatives, right? I want to do some anti-partial derivatives. Why? Because f of x, y, and z is equal to the partial of f on x, the partial of f on y, and the partial of little f on z. It's partial of the parent with respect to y, x, partial of the parent with respect to, with respect to y, and the partial with respect to z, right? Okay, so let's look at the original here. Okay, so this guy, okay, is equal to y squared. Okay, so the partial with respect to x of this whole thing, okay, is going to be of just this component here, of the x component, okay, is going to be what? Well, it's going to be x y squared, right? Make sense? Okay, if I were to, right, so I would say f of x, y, z, right? If I were to integrate this guy, let me write the original right below it so we're not confused. So this is f of x, y, z is equal to y squared 2x minus y plus e to the 3z, comma 3y e to the 3z. Okay, nice. Okay, so let's find the partials of this. Okay, f of x, y, z. Okay, so the partial on this one with respect to, let's actually I'm going to do this. Okay, so it's going to say f of x is equal to y squared. F sub y is equal to 2x minus y e plus e to the 3z. And then f of z is equal to 3y e to the 3z. Okay. I want to take each of these individually. Okay, the first one that I'm going to take is this guy. I want to know, well, what happens when I take the antiderivative of this with respect to x? Now we'll get f of x, y, okay, z equaling xy squared, okay, plus, okay, plus what? Well, plus I could have had something involving a y, right? So like a g of y, or a h of z plus k, or any combination thereof. You know, I could have also a it gets kind of confusing, but we could have a g of z, y, z, any function of y and z, right? And then plus k. I'll just write it like that. Okay. Any function involving y's and z's would be considered a constant, and they would go away. Oh, okay. So what about this guy? Well, that's f of x, y, z is equal to, okay, so now this is just with respect to y. So this is going to be 2xy, right? So 2xy, okay. Sorry. Nope. What did I do wrong here? 2xy plus e to the 3z. Oh, you know what? That's what I was wrong. This is 2xy. Yeah, it's 2xy. Sorry about that. 2xy. Okay. 2xy. There we go. Okay, fixed. Nice. Okay. So 2xy. Okay, so now integrate this on y. Okay, treating x and z as constants. So this is going to be xy squared plus y e to the 3z. Okay. Plus, this could be anything involving x and z would be my constant, right? So I would say maybe h of xz, okay, plus, I don't know, l, j, k, l, whatever. Okay, and then the other one here, x, y, z, okay, this is 3y e to the z, 3z, so 3y just counts as a constant, so it's 3y, and then e to the 3z. Okay, so we're going to integrate that, but if we integrate that, we're going to end up with a 1/3. So this is 1/3 e to the 3z. After we do our u sub, we would end up with a 1/3, which cancels out with the y. So this would be plus, okay, x and y, right? This would be some function in terms of x and y. So this would be, we'll call this L of x, y, plus, I don't know, some other constant, j. Okay, and so, well, what do we got here? Well, let's see if we can put the pieces together. Okay, we have an xy squared and a y e to the 3z, right? Notice that g of yz here is this guy, and L of xy is this guy. Okay, so we have the g of yz as this guy, and the L of xy as this guy. We just don't have an h of xz, but we don't, there isn't one. Because if there was one, we would certainly get that term. You know, if we did some other partial, you know, if we had a term, an xz term, and we did the partial on x, it would show up. Right, it would show up. So this guy doesn't exist. Oh, okay. So the parent function is f of yz is equal to xy squared plus y e to the 3z plus some constant. for a constant, and that's it. Okay, and then if you wanted to do a line integral, you could do a line integral on that as well. Okay, let's go over some definitions real quick. Okay. Okay, theorem. Okay, f dot dr, the line integral of f dot dr is, we say, independent of path. Okay, in D, in our domain D, if and only if the integral, the line integral f dot dr, okay, is equal to 0 for every closed path C in D. Okay, so what does this mean? Okay, okay, that is, okay, so it's independent of path, if and only if. This is what that if IFF means. It means if and only if. Okay, the line integral is equal to 0 for every closed path. What does that mean? That means that there's a closed path from A to A. Okay, so we have a closed path here. Okay, from point A to point A. Maybe I won't make it a circle. Okay, so there's a closed path from point A back to point A. Okay, that when I take that line integral will give me 0, okay, over this curve C. Okay, and what is the domain? It's D. D is in the inside, the curve C is on the outside, and we're going from point A to point A. Okay, so okay, that is how do we define this a little bit better? Well, if I make my, if I put an extra point here, point A and point B, okay, then I can say that as I go from point A to point B, I'm going to call this C1, okay? And then as I go from point B to back to A, I'm going to call this C2, and I would say that the line integral on C1 of f dot dr plus the line integral of C2 okay, of f dot dr is equal to 0. Okay. Okay. Now I could shift some things here. What I could make, think of C1 as going from A to B. That's C1, right? And then we have f dot dr plus, now what's C2 doing? C2 is going from B to A. Okay, B to A of f dot dr is equal to 0. Well, what happens if I flip the limits of integration? If I flip the limits of integration, then I get from A to B f dot dr. Okay, this is going to be, again, C1, but this is going to be negative C1, which is C2. Okay, so negative C1. Okay, if I flip the limits of integration for C2, that's negative C1, right? So this is C1 and this is negative C1, is what C2 is. We're going the opposite direction as the direction that we'd be going from A to B. We're going now from B to A, opposite direction. We're still going along this closed curve though, okay? This closed curve. Okay, so we're going from A to B of f dot dr is equal to 0. Well, what does this tell me? It tells me if I toss this guy to the other side, I get C1, okay, of this should be minus C2, minus a minus. Let me think about this for a second. Plus, no. This should still be a minus. Why is it not coming out right? Because I should end up with C1F.dr, C1F.dr is equal to negative C1, right? Yeah, that's right. Okay, so this should be a positive C2 F.dr. Okay, so as I'm going one direction, okay, that doesn't work backwards. Why is it not working backwards? Okay, so let's go backwards here. Okay, so oh, A to B is not negative C1, that's the problem. A to B is negative C2. Does that make sense? A to B is negative C2. Okay, it's not negative C1, it's negative C2. That makes sense. Okay, that's negative C2, which would make this a negative. Okay, so A to B is negative, is the negation of C2, which would make that turn that negative. Okay, that makes sense. Okay, this was C1, yep. Okay, plus C2 would equal 0, yep. So if I flipped it, it's the negation of C2, yeah. If I flip it, it's the negation of C2. Yeah, and so now put it to the other side. There we go, that makes sense. Okay. Okay, perfect. If it's kind of confusing, you can get rid of that. But it does work out. Okay, I just had the wrong, it should be like that. Okay, because A to B is a negative C2, and A to B is a C1, where C1 is equal to a negative C2. Okay. Okay, next term. Okay, suppose F is a vector field that is continuous on an open interval you know what? On a simple curve. Sorry, no, on an open. I'll just say open interval. No, on an open, simply connected region. Region D. Okay. Let's define open, simply, and connected. Okay. So, okay, what does it mean to be open, simply connected? Okay, let's define that. Let's take a pause. We're going to say that a simple curve is a curve that does not intersect itself. Okay, so a simple curve is a curve that does not intersect. So this is simply a simple curve. Okay, so what's a simple curve that does not intersect itself? That's a simple curve that does not intersect itself. This is a simple curve that does not intersect itself. Okay, any simple curve that does not intersect itself is a simple curve. Okay, what's a simply connected region? Okay, I mean, what would not be a simple curve? Not a simple curve. Okay, that would be like this guy here, right? Not a simple curve. Okay, you do not exist in my simple curve regions. Let's talk about a simply connected region. What's a simply connected region? Okay. Okay, so a simply connected region is a connected region. Okay, so what does it mean to be connected? We'll get to that in a minute. Okay, such that every simple closed curve, okay, every simple closed curve in D encloses only points that are in D. Okay, only points that are in D. Okay, so an example, okay, is this guy. This is a simply connected region, right? Because why? Because this is a simply connected curve. A simply connected curve is a curve that connects itself. Okay, so it's a closed path. Okay, a closed curve has a closed path. Closed curve has a closed path. And a simply closed curve okay, has a closed path that does not cross itself. Okay, so does not cross itself. And so what is a simply connected region? Well, the simply connected region is a region that is contained in a simply connected curve. So we can say this is region D, okay, or the domain, it's inside. And the closed curve is C. We could call this closed curve C. It's kind of like our line integral. We can say, hey, there's a line integral around this simply connected closed region, right? And it encloses our domain D. Oh, okay. And so that is my, okay, it encloses only points in D. So what's not a simply closed or a simply connected region? What's not a simply connected region? Well, what's not a simply connected region would be a region that has holes in it. Okay. We call this region D. Okay. Use a different color. Zoom in and use a different color. There we go. There's D. Okay. And so this has holes in it. So this is not a simply connected region. Not a simply connected region. Okay. Now, why is this so important? Because we just want things that are nice. Because when we go back to our, okay, let's close our parenthetical thought here. Okay. Okay, when we go back, oh, it's all the way back there. Okay, to our theorem here, it says, suppose F is a vector field that is continuous on an open, simply connected region. It just means it's a nice region. It doesn't have any holes or tears or gaps or anything like that. It's a nice region. We say nice region. Okay, and if it has a nice, is over a nice region, and dp dy is equal to dq dx, okay, then what's true? Then, okay, f equaling pi plus qj is conservative. Okay, it's just saying, look, right, if you give me all these really nice things, okay, then this thing is conservative. Well, how do I get all those really nice things? It has to be a certain type of region. I didn't want to gloss over that. I wanted to leave that till the end because I didn't want to get, you know, all bogged down in the details. I wanted to be able to use this right away. Okay, that's 16.3. We'll stop there today. Okay, as always, these notes are posted on YouTube. I will be having office hours from 6 to 6:50. Please let me know if you plan on attending that. You can just send me an email or a text or whatever, so that, you know, because I don't want to sit there if nobody shows up. So, but if you need help, I will be there in 35 minutes. Okay.
Bye. Thank you.
Thank you.
Professor, quick question. I was looking at WebAssign and it showed that 16.3 is due tomorrow at Thursday. I'm not sure if you addressed that earlier in the class.
Oh. Oh. Yeah. Let me change that. That should
Cool,
be.
thank you.
That should be due Monday. So, okay. Thanks.
Thank you, Professor. Have a good one.